It's my pleasure to welcome Alvise Trevisan, who will speak to us today about, from the Free University of Amsterdam, who will speak to us today about real quasi-toric manifolds and their homology.
Okay. Thank you. Thank you for inviting me. It's a pleasure to be here. It's an honor to be here. So, let me mention first of all that this is joint work with Alex Suciu. Joint work with Alex Suciu. It's also partly work in progress. And okay, I'll be telling you about real quasi-toric manifolds. So, what's the motivation for this? How do these manifolds originate? And basically, the motivation starts from the theory of toric varieties. So, a toric variety, let's say, toric variety X. So, in its simplest form, it's an algebraic variety with an action of the complex torus. Yeah. Satisfying two conditions. So, such that first of all, it contains this complex torus as a dense subset. So, X contains is a dense open subset. Yeah. And the second condition, we want this action to extend the natural action of the torus on itself. So the complex torus acts on itself by multiplication. And we want this to extend to this action. Yeah. Yeah. Right. So in its simplest form, a toric variety can be described in this way, and doesn't look impressive, but actually just these two conditions give a lot of structure to the variety. So you can explicitly, okay, how can I say it? For example, let's see. If you take the compact torus, so just the product of circles. So this sits inside the complex torus. And if you just restrict the action to this compact torus, then the orbit space is a polytope. Well, not always, but let's see if X is smooth and projective, then this is true. So, and more or less one of the main themes of the theory of toric varieties is that you have this interplay between the combinatorics of the polytope and the algebra and the geometry of your toric variety. So maybe one more interesting thing that you might know is that actually all toric varieties arise from a certain combinatorial construction. You basically start from something called a fan, which is a collection of cones, objects in Euclidean space. So something like this. So let's say this is the origin. And basically, you can show that every toric variety can be built from this object by first building smaller, affine varieties corresponding to these cones, and then gluing everything back together to get your toric variety. Toric varieties, yes. Oh, every complex projective space is a toric variety. Hirzebruch surfaces. Yeah, I mean. So, okay, so actually, okay, the main object of this talk will be about real quasi-toric manifolds. So let me write it explicitly, real quasi-toric manifolds. So I'll first tell you what a quasi-toric manifold is, and then try to, and then try maybe to speak about the real part of such manifolds. Yeah. So let me start. So there are a couple of equivalent ways to define this. I'll start from the most combinatorial version. So you start with a simple polytope. So a polytope is just the convex hull of a finite set of points in Euclidean space. So it's something like higher dimensional analog of a polygon. You start, n refers to the dimension here. So of dimension n, and with m facets, and the facets are just the codimension 1 faces. So the data is a polytope and a characteristic matrix. So simple means that each vertex is the intersection of precisely n facets. So for example, polygons are simple. So each vertex, so this is 2-dimensional, and each vertex is the intersection of precisely 2 edges. So those are the facets in this case. That's what simple means. So and then we say that chi, a matrix, let's say, let me put it this way. Sometimes I think of this as a map. So it's an n by m matrix with integral coefficients. And we say that this chi is characteristic for P. If it satisfies a certain condition on its minors. And I don't know if I want to write down this condition. Well, maybe I will anyway. Let's see. I'll just write it down. It's not important to remember what this is. So if whenever, let's say, fi1 whenever n facets meet at a vertex, so whenever n facets meet at a vertex of P, then the corresponding columns in this matrix form a, okay, let me write it down. So the minor given by the columns I1 to In is unimodular. So it has determinant plus or minus 1. And so in particular, this matrix has maximal rank. But okay, it's not really important. It's just the conditions on the minor. And it essentially, we'll see when we get to the manifold, it's a smoothness condition. So how does the construction go? So we have everything in place. So we take, again, the n torus. So just S1 to the n. And we first take the Cartesian product of that torus with the polytope. And then we identify certain points in this space. And this identification, again, I'm not going to write it down, but essentially, okay, let's see. The identification, okay, identifications, they occur only on the points lying above the faces of the polytope. So identifications occur only on points lying above the faces of P. And these identifications are dictated by chi. So let me maybe draw a couple of easy examples. So the first example is maybe the sphere. So let's take P to be just the interval. So this is more or less the only one-dimensional polytope. So n is 1 and m is 2. M is the number of facets. So 2 vertices are the 2 facets. What do we do? So we cross it with T1, which is just a circle. So we get this. So we get this cylinder with a boundary, with 2 boundary circles, and then in this case the identifications, as I said, they occur. Okay. They occur over the point lying above the facets. So in this case, the identifications occur only on the boundary circles. And so in this case, you just identify each boundary circle to a point. Okay, so this is, well, maybe not a, this is just a sphere.
chi in this situation?
So in this situation, there's essentially just one chi. So up to diffeomorphism, for example, this one. So again, as I said, it's an n by m matrix, so it's a 1 by 2 matrix, and it's more or less. You can also take this one, or -1, doesn't matter.
So you also should do each facet an n vector.
Right, yeah. Let me write it this way. If the polytope is an n simplex, so this is just, we can think of this as the one simplex, right? Over the n simplex, there's only one. Actually, let me also add one extra piece of notation. I will call this MP of chi. So it depends on the polytope and on the particular characteristic matrix. So over a polytope, there might be different characteristic matrices. And then different manifolds, quasi-toric manifolds. So for example, over a simplex, there's only one quasi-toric manifolds, and that's complex projective space. Or let's see other funny examples. So we can just keep that in mind. Over a square, you have essentially 3 up to diffeomorphism distinct quasi-toric manifolds. You can have either a product of spheres, you can have connected sum of CP2s, or you can have a connected sum of CP2s, but one of them with the opposite orientation.
I'm confused. What does this chi have to do with the definition?
Oh, yeah, okay, that's a good question. So essentially, roughly speaking, this dictates the way you identify these facets, but maybe I can also be more precise. Essentially, so it's okay. I'll be more precise a little bit later on, but it specifies the way you identify these points in this product. Yeah.
Maybe you should, before you guys do a picture with the facts.
Yeah.
Vectors are associated with that.
Okay. Yeah. Maybe. Okay. That's a good suggestion. Maybe I'll do that. So if you know about the theory of toric varieties, so let me do this. Let me just do this. So just a connection. Okay. Let me remark this, and then I'll give you one more example. So if X is a smooth and projective toric variety, then X is also a quasi-toric manifold. So this class generalizes, not generalizes, but there's a big overlap with the class of toric varieties. And for example, if you know about I'll do this example for the people who know about the theory of toric varieties. Let's say CP2. So the fan for CP2 is something like this. It's in 2-dimensional Euclidean space, and it has the following form. So this is 1, 0. This is 0, 1. And this is -1, -1. And the fan consists of these 3 portions of Euclidean space, these 3 cones. And essentially what you do, you associate to each of these cones a C2, this is a fine variety, and then you glue them all together to get CP2. And, well, how do we see that this is a quasi-toric manifold? This is the general idea. You take the edge vectors, and your chi will be this. So each of the 3 edge vectors is what constitutes the columns of your chi matrix.
And P?
Oh, P, yes. So P in this case is the 2 simplex. And here, for example, what you can do is you can take the, you can take the cone here. Well, that's in this example it does work. So that's what happens. So this is delta 2. Yeah. So maybe one more word. yeah, one way to do that is precisely that. You take the inner normal vector to the fan, and then what happens? Yeah, that collection gives you a polytope. Okay, so
So for example, that square there for P, two of them are of that nature, right? The
Mhm.
first and the third.
yeah, so okay. Let me go. Yeah. So yeah, in this case, okay. What as it happens, let's see. This. So this is also a toric variety, and this is a toric variety, just by the same construction. But this turns out not to be a toric variety. For example, this one does not admit a complex structure, whereas these toric varieties are smooth and they're projective, so they all have a complex structure, a canonical complex structure, and this one does not admit one. So they have an overlap, but they're not precisely the same class. Yeah, why do people wanted to study them anyway? I think the input for these quasi-toric manifolds came in the early 90s. So 1981, Davis and Januszkiewicz published a beautiful paper in Duke. Yeah, I'm not sure where whether the Z's go before or after. It's all right. Yeah. Yeah. So they published this very nice paper on Duke Mathematical Journal, in which they realized that a lot of the properties of toric varieties that have been studied a lot, they're essentially topological. So they do not depend on the geometry of the variety. They actually depend only on their topology. So that motivated them to introduce this class of manifolds. Yeah, so that's more or less, this gave the input to the study of quasi-toric manifolds. Okay, yes, so maybe that's all I wanted to say for now about these quasi-toric manifolds. I'll tell you about the real part of such manifolds. So I'll first give you a very similar construction, and then try to motivate a little bit why this is relevant. So again, we start with Pn, a simple polytope with m facets, but now we take a characteristic matrix to be something over with mod 2 coefficients, with coefficients in the field with 2 elements. And this has to satisfy the same condition on the minors, satisfying the same condition. Same condition. And so what you do, you take the circle, and you just take its two torsion points. You take 1 and -1. So let me call this T2. And you carry out the same construction we did before, just by using these two torus instead of the whole. I mean, these 2 points instead of taking the whole circle. So what you do, again, start with a polytope. You cross it with this discrete set, and then you identify certain faces. I mean, certain points lying above the faces. And this I will call NP of chi. And let me do the analog example. If you start with an interval, well, this is one-dimensional, n is 1. So you basically just take the interval crossed with ±1. So you just take 2 copies of the interval. And here the identifications occur again only over these 2 points. So you end up with a nice circle. And just as before, for example, if you have this, okay, the chi for this is, for example, 1, 1. If you start with a simplex, then you end up with RPN. And what did I do? The square. Over the square, there are 2 different small cover. I mean, okay, this is also. So another name for this is small cover. small cover. I will use it just in the same way. Small cover is the same as a quasi-toric manifold. And over the square, you have essentially two things. One of them is a product of circles, so just a torus, or a Klein bottle. Yeah, and just as before, there's again a connection with toric varieties, and it goes as follows. So if X is a smooth projective toric variety, then if we take the set of real points of the variety, its real part, this is a real quasi-toric manifold. And yeah, and again, the overlap is pretty large, but it's probably not, yeah. Okay, so far so good.
So with the square, how about for an M block?
Mm-hmm.
Interesting. You get
Yeah.
surfaces.
Yeah, you actually you get, yeah, with any n-gon, so you can get all surfaces of a given genus by this construction.
Orientable and non-orientable.
Orientable and non-orientable, sure. Yeah, in the two-dimensional case. Yes. Okay, so let me give you a couple of properties, so then maybe I can answer your question about how do you identify those faces and how does the chi come into play, the characteristic matrix. Let's see, some properties. Let's see what I want to say. So M. Okay, let me actually start this way.
Except S2.
Hmm?
Except S2.
S2.
The sphere.
Mm-hmm.
I don't think you get RP2 and the torus and the Klein bottle, but I don't think you get S2.
No. Ah, okay. S2 would be. No. Yes. No. You cannot get S2. Yeah. You're right. Yeah. You cannot get S2 by this construction. So. Yes. So let's consider this quasi-toric manifold again. So again, the construction will go something like this: polytope, cross torus, modular identification. So what happens is that the torus acts on itself by multiplication. So we can extend this to an action on this product just by letting this act trivially on the polytope. And then you can show that it descends to an action on the corresponding quasi-toric manifold. So just as in the case for toric varieties, those things come with an action of the torus, which extends the natural action of the torus on itself. And actually, you can say something more. So maybe this is the first thing I want to say. By construction, if you take the orbit space, then this is just by construction the polytope. That's the other interesting thing, and actually even more. So there's a correspondence between the faces of dimension k and the orbits of dimension k under this action, and the k orbits. So, essentially, okay, chi is this matrix. So the idea is essentially that you, okay, yes. So the columns of this matrix specify the stabilizers of this action. So more or less, the idea of this characteristic matrix of the whole construction is that you specify the space by telling them what are the stabilizers in each dimension. So that's more or less the idea. That's how the chi comes into play. It tells you at each point what is the stabilizer, what is the orbit. So that's one way to answer your question. Okay, well, maybe that's all I want to say. And yeah, if you just put a 2 there below your t and then below your z, then you get the same thing for the real quasi-toric manifold. Yeah, so
So these are like T and bundle of a polytope, kind of singular along the
yeah,
face of the polytope, and the other ones are like covers, right? Like Z2 and
yeah, more or less, yeah. Yeah, so let's see. I'll tell you a little bit more about these spaces. So as I tried to motivate before, there's an interplay between the combinatorics of the polytope and the geometry of these spaces. So let me start to delve a little bit into that. And so P, so if you have a polytope P, so you have an F vector. This F vector is simply a tuple, an n tuple of numbers. And Fi is the number of faces of dimension I. So this is one of a basic combinatorial object. And from this you can get something called the H vector, which is equivalent to the F vector. And yeah, I don't even want to tell you how to get from one to the other. But anyway, once you know this F vector, you also know the H vector. It has the same length. And so this is a combinatorial invariant of the polytope. Combinatorial invariant of P, in the sense that, yeah, so any map sending a polytope to another polytope and preserving the faces and preserving the face lattice will also preserve this H vector, obviously. But why is it important? So because I want to tell you about the homology and the cohomology of these spaces. Yeah, so I want to tell you about the homology of these spaces. It's a cohomology. Okay, let me write it down briefly. I'll do the complex and the real case at the same time. So in the complex case, you have the odd dimensional homology vanishes. I'm talking about homology with cohomology with integral coefficients. Whereas even dimensional groups are free and they have rank h to the I. So they depend on the polytope and only on the polytope. And in this case, just get that hi of n with z2 coefficients is free as a z2 module and it has rank hi. So this is already striking in a sense, because here you have over a polytope you might have a big number of different manifolds, but for some reason their cohomology, at least additively, depends only on the polytope. So whichever polytope you pick, any quasi-toric manifold on top of it or any small cover will have the same additive homology or cohomology. So this is already an interesting fact. And well, actually, so we even know the cohomology ring of such things. And this is something like this. It's an affine algebra. It's a quotient. Well, it's not an affine algebra. It's a quotient of a polynomial ring. So it's something like this. So the
this is the complex and the real.
Yeah, I understand, but the n sub I normalizes what?
H sub I, the H vector.
Oh, that's an H. Okay.
oh yeah, sure. So that's h, and that's the ith coordinate in the H vector. And well, this has the same shape. This is isomorphic to here I talk with z2 coefficients. This is a polynomial ring modulo a sum of ideals. So let me point out. Yeah, so here this only depends on the H vector. So only depends on the number of faces of the polytope. So it's a very coarse invariant of the polytope. It's only the number of faces. Whereas this cohomology ring has a part This depends only on P.
So this is Stalin-Reisner.
Yeah, Stalin-Reisner ring of the dual simplicial complex. So the simplicial complex dual to the polytope. And this depends on chi. So this is okay. This is generated by linear forms and depends only on chi. So you have a part which is only combinatorial and a part which depends on the particular characteristic function you chose. And yeah.
Can different chi's give you the same J chi?
I mean, that's just given that the
Yeah.
also the matrix. But when you
I mean,
add it and you take it, the quotient maybe.
The different J. Oh, well, the same ideal. No. Well, if they give you the same ideal, more or less it means that they come from the same characteristic function. But what happens is that.
You just kind of sum the rows.
Mhm.
The summation of chi xi.
Yeah.
We can say that's the same question about the sum of the ideals.
But yeah, I think that's a question. Maybe.
No, I really.
Different
He just said that it's generated by some linear forms. Know which ones.
Yeah. Sure. No.
Maybe it's a nice to.
I don't. Well, anyway.
You want to do an example? Or?
No. Well, it's. No. Let me do an example at the end because otherwise, I mean, I can just write down a polynomial ring and two ideals, and it's.
We should just. I mean, in the for toric varieties, this is this Zhorkevsky or Danilov.
Yeah, Danilov. Yeah, this is due for toric varieties. This is due to Danilov and Yurkevich. Yeah, but it's only for a smaller subset of manifolds. This is true for every of these quasi-toric manifolds. Okay, so why did I tell you this? Because this was more or less trying to tell you what these spaces are, and I want to tell you what me and Alex have been working on. So about the integral homology of these spaces, because it's everything is known about Z2 homology and cohomology, but there's not much which is known for integral homology, and I think so. What turns out to be the integral homology is very interesting, and there's again this interplay between the combinatorics of the polytope and the characteristic function, but it's a little bit more complicated than this. It's a little bit more subtle. Yeah, so maybe. Okay, this is also maybe a good time if there are any questions or remarks or suggestions. Okay, no. Let's keep going.
I think an example would be nice, like how to distinguish these rings. For example, let's say what would be the simplest one? The one with P1 plus P1 versus P2 blown up, right? I mean, those two examples.
Okay,
It's a square, right?
let's do that.
Is it difficult to do?
No, it takes a second.
Very long.
Yeah.
Just me?
No, no.
Example would be good. Examples are
Don't worry.
Yeah.
Well,
Sure, no.
What?
No, okay. Yeah, sure. I'll give you this example. Maybe I'll just cut a little bit on the proof. I'm not sure how many people are interested in that. But okay, so let's start from a square. And okay, let's number the facets in this way. So as I said, okay, I want to look at these two spaces. S2 cross S2. And a connected sum of CP2s.
What are real points, right?
Well, it's the shape is the same, so it doesn't really matter. So okay, no, maybe you're right. So maybe I'll use this example later on. Let me do this. Let me do the real part. So the real version of this. So this particular chi matrix specifies the torus, a product of circles, and this particular chi, maybe this, specifies, so this gives rise to let me call chi and chi prime. This is the Klein bottle. So using that recipe, the cohomology ring over with Z2 coefficients is given by Z2. Well, we know what this is, but let me just write it down using this formula. So this ideal is generated in the following way. So you take a monomial, this IP. So you assign a variable to each facet, and then whenever two facets don't intersect, then you take the corresponding monomial, the corresponding product. So for example, in this case, 1 and 3 do not intersect. So you take the product of x1 and x3, and the same is true for x2 and x4. So this is the IP. It's called Stanley-Reisner ideal of the polytope. And then the linear forms, you just take the sum of these rows according to the variable. And by that I mean you take x1 plus x3 from the first row. So you have a 1 here, so that's x1 and that's x3. And you have x2 plus x4 from the second row. So so this is just Z2 is isomorphic to, let's say, xy modulo xy squared, x squared and y squared, which we all know. I mean, this is just a product of circles. So that's more or less the way it goes. And for the Klein bottle, well, you do the same thing, and then you end up with the cohomology ring of the.
Different ring, right?
Yeah, sure.
So you have like an XY or something.
Yeah, yeah. Well, the cup products have to be different, right? This is, yeah.
No, actually.
Yeah.
Yeah. But the Hilbert series is the same thing, right?
Yeah. So, yeah. Okay. Yeah, so let me, what can I say?
We started about 10 minutes.
A little bit later. Okay, good. So let me try. So I want to talk about the integral homology. Actually, like maybe I just focus on the Betti numbers, so I can give you something explicit. Betti numbers of small covers of these NP chi's. Yeah. So let me just write. Okay, I'll focus again on B1 just to give you an explicit formula. So I'll just write it down for you to give you an example of the sort of interplay between combinatorics and topology, and then maybe I'll try to motivate it. So let me just introduce a couple of things. So if you have a subset I of, so a subset of indices, a subset of y1n, and we name, so we say, so chi is a matrix, so we call each row, so we call the first row chi1, the last row chi-n, and so on. So in this case, this would be chi1, this would be chi2. And then we set chi-i to be the sum of all the rows dictated by this I. And then we say that the support of one of these chi-i's is the set of all coordinates that are non-zero. So it's different from 0 in this characteristic thing. So for example, the support of this row would be 1 and 3. 1, 2, 3, 4. The support of this row will be 1 and 3. So this is a subset of 1 to the m. And yeah, so actually let me state this in terms of P. So each polytope has a dual simplicial complex. So this is the dual simplicial complex. I don't think I want to go into the details of that, but anyway, so this is this object is a simplicial complex related to this, and it reverses the dimension of the faces.
With vertices or faces.
Yeah, so facets, for example, in this case, the dual simplicial complex, okay, maybe I just tell you. So what you do, you put a vertex for each facet of your polytope, for example, and then whenever two facets intersect, for example, 1 and 2 here, then you draw a simplex between the two vertices, and so on. So that's the dual simplicial complex. And so let me state what the first Betti number of a small cover is, to give you, so I mean integral here. So this is the kind of flavor.
This would be a triangulation of the sphere in this case.
The dual simplicial complex would be a triangulation of the sphere, sure. And okay, that's even interesting from the combinatorial point of view. If you have a triangulation of the sphere, you want to know whether or not this comes from a polytope. It's a dual of a polytope. And people do not know that. It's one of the basic.
It's not true in general.
No, it's not true in general, but for example, people would like to find conditions for that to be true. And that, or an algorithm or anything, and people don't know anything about that. So it's a very deep problem, I guess. And then it's been open for a good number of years. Okay, yeah, so the first Betti number is given in the following terms. You take all possible subsets of 1n. Then what you do is the following. You take the induced subcomplex. Okay, so you first take the support of chi I. So this is a subset of the vertex set of k. You take the induced subcomplex and you compute its reduced simplicial homology. And so you do this for each of these i's, and then you sum up everything together. So this is simplicial homology. This refers to simplicial homology. Okay, so the idea is that more or less, so you do some sort of local computation. You first identify a number of subcomplexes of your simplicial complex, of your polytope, and you compute just their simplicial homology. So you do this sort of computation locally, and then you sum up everything together, and you come up with a solution. So this is...
I'll show it on these examples.
Yeah, let's do that, why not? Yeah, so let me, let's see, I can erase this. Let's do the torus, for example. Well, I mean, these are all small examples that if I have 5 minutes in the end, I'll do something more satisfactory, probably. So 1, 2, 3, 4. Yeah, so this is the dual simplicial complex. I erased it, I shouldn't have done it. Okay. Yeah, yeah, that's true. Yeah. Okay, so here we have n is 2, so we have 3 possible choices. We have chi1, chi2, or chi1 plus chi2. So these are the 3 chi's appearing in this sum. So this is the first row, this is the second row, and this is 1, 1, 1, 1. So so the support of chi1 here is 1 and 3. The support here is 2, 4. And here every coordinate is different from 0, so the support is 1, 2, 3, 4. Okay. So what's the induced subcomplex here? The induced subcomplex in this case, so you take the 2 vertices. So the induced subcomplex is just the 2 vertices itself. So it's 1, let me just draw it. 1 and 3. And in this case, the induced subcomplex is just these 2 vertices, 2, 4. And here, since the vertex set is the same as the one for the simplicial complex, the support is k itself. So it's the whole square. And now, well, so we compute the reduced Betti number of all these 3 things. And that's, so the, yeah. comforting. So that's how it works. And actually you see, for example, well, let me put this, bi minus 1. You will see that, for example, in this case, you compute the first Betti number, and the only thing giving a contribution to the first Betti number is this. So you get 1, which, comfortingly enough, is the second Betti number of the torus. Anyway, so this is, yeah. Let me put it as a theorem. I don't know. Why not? Yeah. So maybe I'll spend 5 minutes telling you how to prove this. At least not how to prove it, but at least what goes into the proof. And then maybe I'll do a last example, and then I can stop. Not really.
It should, does it sound like a Hoxton formula to you? Does indeed? I mean, it's
Looks like that to me.
analog in the part of the Hoxton formula. Okay.
Yeah. So, okay. What's the idea? So what's the idea? You start with your small cover, your real quasi-toric manifold, and at least up to homotopy, this sits in a fibration with a certain space, which I will call djk. And the base space of this fibration is the classifying space of Z2 to the n. So this
When
is.
you say vibration, what do you mean? Surf vibration, a locally trivial vibration?
Surf vibration. Yeah. So this is space. Okay, this is actually a funny space. It's I mean, lots of people thought about it. It has a lot of interesting properties. Again, this Januszkiewicz. So it's a real Davis-Januszkiewicz space. Let me put it like P. Space of P. And this is actually, by looking at this vibration, so looking at this vibration gives you the computation of the cohomology ring. So this is where this combinatorial part, which was on the blackboard before, well, it's maybe you cannot see it anymore. So the part, this depends only on P, and the part of the cohomology ring that depends only on P comes precisely from that space. And it's also an example of a moment angle complex. But yeah, I don't think I have too much time to tell you about that. Anyway, so this space sits into this vibration. And
The homotopy fiber, right?
yeah, up to homotopy, sure.
It's actually inclusion.
Yeah, up to homotopy. So this is actually, okay, up to homotopy, it's the Borel vibration of this space. So Borel vibration, whenever you have a topological group acting on a space, then you have bona fide vibration, not just up to homotopy of this form. So yeah, this is the universal space of G, and this is the classifying space of G. So it's called the Borel vibration. And up to homotopy, that vibration is precisely this Borel vibration. But anyway, okay, so we have this vibration. We look at the long exact sequence of homotopy groups. So pi 1, let me just call this n. Pi 1 of n, pi 1 of dj, pi 1 of that is just z2 to the n. And that is a k pi 1 space, so we have a 1 here on the second homotopy group. So we have a short exact sequence. So essentially we're identifying the fundamental group of n with the kernel of a certain map, right? So we're identifying that group with a subgroup of P1 of dj. Okay, so you can say, well, you can say a little bit more. So this is actually a composition of two maps. This is the abelianization map, and this is the characteristic, Z2. But, okay, it's not.
Tell us what that group is, prime DJ.
Yeah. Okay. Sure. Okay. This is very well known in group theory. So this is called a right-angled Coxeter group. Right-angled Coxeter group, and it's finitely represented, and lots of people studied it for other reasons. So it has a presentation given by M generators, so where M is the number of facets, and then you set the squares of generators to be 1, and then you have a commutator xi xj whenever ij is in this dual simplicial complex. So yeah. Yeah, of course. I mean, this only depends on the graph, on the one skeleton, the simplicial complex. Okay. Right. So we identified this with the kernel of this map, but we know there's a correspondence between regular covers. Okay, maybe we know that a regular z2 to the n cover, abelian, some people say, z2 n cover of dj is specified, so is in one-to-one correspondence with a group homomorphism from the fundamental group of the space to z2 to the n, right? So group homomorphisms onto z2 to the n correspond to abelian covers of dj with this group acting as with that group acting. And so by working a little bit, turns out that so the regular cover corresponding to our map, to this map, let me call it chi bar. The regular cover corresponding to chi bar. It's not too hard to show that this is actually homotopy equivalent to our original real quasi-toric manifold. So yeah, we identified this real quasi-toric manifold with a regular cover of the base space. So just say a couple more words, and then I'll save some time for an example at the end. Good. So what's the general idea to compute now the homology of that, since we have a cover? So we compute. So okay, let's do it this way. We take this dj sitting there. We take the universal cover, and we compute its chain complex. And we see this as a complex of z pi 1 of dj modules. So we see this as a chain complex of modules over the group ring over the fundamental group. And so to obtain, and the homology of the cover is computed by this chain complex with tensor over z of pi 1 dj with this group quotiented out by this group. So this is general theory of covering spaces and homology with coefficients. There's nothing deep going on here. So if we do this, if we compute this chain complex, we tensor it in the appropriate weight, then the homology of this will be the homology of n with z coefficients. So that's more or less the general idea. But the thing is that this tends to be complicated. It tends to be untractable. So if we actually work over the complex numbers, since we're interested in embedding numbers anyway, so we could as well work over the complex numbers. So if we work over C, then something happens. And what happens is that this group ring, if we split, so basically we see this group ring as corresponding to the regular representation of Z2 to the n. And from the representation theory of finite groups, this completely decomposes as a sum of reducible modules taken with multiplicity. So let's say rho is a irreducible representation of z2 to the n, and rho is the multiplicity of the representation. So it decomposes in this way, where these are representations, C representations of C. So rho is a C representation of z2 to the n. So this big chain complex, if we work over C, it is split in as a direct sum of smaller representations. And actually, since z2 to the n is a billion, then all these representations are one-dimensional. So essentially, going back to our formula, I said something like we compute locally, and that locally comes from this. So we split this big ring in smaller representations, and then each of these gives rise to the local computation I was mentioning before. So that's more or less the idea of the proof, and maybe that's all I want to say about the proof without going too much into the details. Yeah. Okay, so I'm almost done, I think. I just want to give you a nice picture and a last example, and then I'll be done. Yeah. Okay. So I'll draw on the blackboard a dodecahedron. So P is a dodecahedron. So yeah. Guess you can count as soon as I draw it. Okay. This is always fun. It has all pentagonal faces. Well, should have started a little bit more to the right, but never mind. It's like a soccer ball, more or less. Right? So we're watching a dodecahedron from above, and we're squeezing it onto the blackboard. And the only face we cannot see is the back one. So this is our P. And actually, okay, let me. So I will write down what's the homology of all the possible small covers over this polytope. This is actually, it's also fairly interesting. There's a number of spaces related to our small covers sitting on top of it, and they provide an interesting class of examples. For once, let's say. So this manifold. Okay, let me write it down. So P, since it has only pentagonal faces, can be realized as a right-angled polytope. So a polytope with only right angles in hyperbolic space. So with just a little bit of work, what happens is that every small cover sitting on top of it is hyperbolic, has an hyperbolic structure. It's an hyperbolic 3 manifold, actually. Let me also specify this, right? So this is 3-dimensional. So any small cover will be 3-dimensional. And so every small cover on top of this will be a hyperbolic 3 manifold. Yeah. So let's see, n is 3. The number of facets is, well, guess is 12. Yeah, so I said before that, okay, hi of n with z2 coefficients, this was already known. Let me write it. So it's specified by the h vector. So in dimension, so h1 with z2 coefficients, okay, is z2, okay, h0 is z2, of course, h1 is z2 to the 9th, H2 is Z2 to the 9th again, and H3 is Z2. So this is the additive structure of any small cover sitting on top of it. Then the actual cup product will depend on the characteristic matrix.
So 9 comes from?
9 comes, well, that's, okay, so let me put it this way. H is, the H vector of the polytope is 1, 9, 9, 1. That's where it comes from, but in the 3-dimensional case, there's actually an easier way to count, and H1 is just m minus n. So in this case is 1, okay, 12 minus 3. Okay, so 3 manifolds. 3-dimensional small covers are maybe a little bit more special than the others. So 3-dimensional small covers have at most 2 torsion, so they have no odd torsion in their homology. So showing that they have no p torsion, it's easy. It's a transfer argument, and showing that they have no 4 torsion is not so trivial. But at least for 3 manifolds, we did it. Well, I mean, it can be done using Bochsteins. But in any case, they have at most 2 torsions. So that means that the Betti number of any such cover can be at most the mod 2 Betti number. Which in this case is 9. So the integral Betti number can be at most this, can be at most 9. And actually, okay, there are up to equivariant diffeomorphism, there are only 25 different characteristic functions. So there are 25 of them. I'm not going to write them down, but yeah, the matrices are pretty big. Yeah. But there's, okay, so I drew a little histogram of the distribution. And actually it turns out that the highest Betti number in all these possible small covers is actually 4. So the bound is not attained. It's, yeah, so anyway, 1, 2, 9, and 12. So this is how it goes. There's 1 small cover with Betti number 0. There are 9 with Betti number 1. There are 12 with Betti number 2. There is 1 with Betti number 3. And there are 2 with Betti number 4. And I guess, does it add up to 25? Yes, okay. So this is how they are distributed. So, yeah. That's the way it is. There should be something where, I mean, this is work in progress, part of it. So we're still thinking about a good way to identify this bound, so why this happens. And it has something that has to do with the structure of that polytope. And, yeah, I guess you'll have to wait to know about that. Okay,
Right. Thank you.
That's it.
Are there questions? We have plenty of time, unless you need to run. Alex already asked lots of questions, and he's grinning at Tony. He clearly wants Tony to ask a question. Are there questions?
It's a strange shape. I mean, as a sequence of numbers.
Yeah, but okay, so I think there are philosophical reasons for the Betti number of a manifold to be low in general. They tend to be low. In this particular case, yeah,
I mean,
it's a little bit surprising.
This Betti number actually gives the whole homology, right? By concurrent logic, so we know
Mm-hmm.
the idea would be.
Yeah.
Is there any hope of getting your hands on the other integral Betti numbers, or the other Betti numbers?
Yeah. So.
That's what you're working on.
Yeah.
Yes.
Yeah.
Yeah.
And
That.
will the next easiest be B2 or at the other end?
No.
We just do the whole thing.
Yeah.
We just
Just do it at once. But the formula should be just precisely the same. Just replace 1 and 0 with I and I minus 1. So that's.
So, can you write code to calculate these things?
Hmm.
Yeah.
We did actually.
Mathematica?
Macaulay.
But also use some gap and stuff like that.
Yeah, well mixed, sure, yeah.
I mean, still, I mean, it's principle is doable, but it's still kind of how to write all these skies. So
Oh, yeah, that's another
so
funny
it's
problem.
just purely algebra question, right?
Yeah, sure. Even the fact that,
The 25 different kinds?
yeah,
Right. So you have
Right.
yeah.
how many? You know, what is the size here?
So it's a 3 by 9 matrix. No, 3 by 12. Sorry.
Wait, how many would that have this condition on the minus?
With these two coefficients satisfying that condition, and still you have to mod out by symmetries of the polytope because they will give rise to the same thing. So yeah, I don't know how
This
to do it
was
in
actually
general.
done by there was a project, right? I mean, this was done by some other people. This 25.
That alone was big.
I mean, they had a paper. That's what they did. Is kind of covered.
Yeah.
But it's,
The new, I
but
mean,
it is just
they,
kind of fundamental, basic linear algebra.
Yeah, yeah,
or
yeah.
something.
But
yeah.
Right. Yeah, somebody has to do it, I agree.
it's not done. Yeah. Can you do it?
Sure, it's just not worth my time. Undergrads can do that. I'll let you, or you can do it. Are there any other questions or comments? All right, well, let's thank the speaker again.
Thank you.